Hello everyone, I am Soumyakant and I am here to present our work on binary instrumentation. So, we developed a platform called Sekar for efficient and error tolerant binary instrumentation. So, to give you a brief overview about what binary instrumentation is, it refers to the process of modifying a program without having access to the source code. So, binary instrumentation provides some unique capabilities like securing hardened deployed software. It also helps in program profiling and debugging as well. So, the key challenge in binary instrumentation is the problem of interpretation. Without any symbolic information, it is hard to say what is data and what is code in a binary. Since binary instrumentation expands or changes the code layout of the program, we need to correctly identify all the code pointers and update them so that we can generate a functional binary. So, to sidestep this problem of translation, many recent techniques rely on dynamic translation. So, what they do is they generate a pointer map statically, and at the runtime, just before an indirect control flow transfer is done, a translation routine is called that looks up the old pointer to find a new pointer. However, this process can have high runtime overhead. On the other hand, static translation is prone to error. So, in this work, we try to find a way to combine both static and dynamic pointer translation so that we can have best of both worlds, that is performance benefits of static translation with correctness of dynamic translation. So, how do we do this? So, first of all, we identify a set of pointers that are more likely to be code pointers. Given a set of more likely code pointers, we pre-translate them and others are allowed to go through runtime translation. Now, the key challenge here is how to distinguish the two types of pointers at the runtime. So, we rely on pointer encoding to do this. Specifically, we flip or change the most significant bit of a pointer, and at the runtime we check that if a pointer is encoded, we then decode it and use it as it is, or else the pointer is allowed to go through runtime translation. Now, what if we have error in pointer classification? Say we have misclassified a data pointer as a code pointer. Now, since we are flipping the most significant bit of the pointer, it is now pointing to an unmapped segment of the memory. Now, whenever the program tries to use the pointer to read a memory, it will crash. Now, the next challenge is computed code pointers. Say a program is using one code pointer to identify or compute another code pointer. Now, since the binary layout has changed, all the old pointer arithmetic is no longer valid. So, we need to identify this and update this. However, identifying pointer computation statically is hard. So, what we do is we try to detect it at the runtime and try to abort or halt the program in case it occurs. So, what we do is we rely on a new multiplication based encoding. First, we choose two odd random numbers that are multiplicative inverses of each other, so here we have two odd numbers a and b, such that when a is multiplied with b, we have 1. So, encoding simply involves multiplying the pointer with a, and decoding involves multiplying it back with b. Now, say the now the program is trying to do some arithmetic computation on the encoded pointer. Now, in this case, multiplying with a large odd number b will throw the new pointer to an unmapped memory segment, and this will again result in a crash. So, what if the program frequently uses computed code pointers? So, jump tables are one such case. Now, imagine every time a program uses a jump table and the program is crashing. So, that will not be ideal for our case. So, what we do is we try to identify the jump tables and try to recreate them. So, for identification, we rely on static analysis similar to other techniques, but our main contribution is how to safely transform a jump table. So, what are the challenges in translating a jump table? First, the safest approach will be to put the jump table in through runtime translation. However, as we discussed earlier, this will have high overhead. Now, the second approach will be to just update the jump table in place, but in that case you need to correctly guess the bound or size of the jump table, or else we can end up overwriting or corrupting other data. For this reason, we have come up with a new approach where we keep the original data intact, we recreate the jump tables and change the jump table access. However, this comes with a new additional challenge. What if the jump table address is being used for other purposes? For example, we found in many programs the jump table address was used to access other adjacent or neighboring data objects. Therefore, we come up with a static analysis that tells us whether a jump table is safe to translate or not. Specifically, we try to detect if the jump table address is being used to access any other memory other than the jump table itself. Additionally, if the jump table address is being written onto heap or is being passed around as a call argument or a return value, it is hard to predict its usage. So we identify such jump tables as unsafe. Our analysis is able to mark 83% of jump tables as safe, which allows us to avoid address translation for a majority of jump tables and improve performance overhead. Now, in evaluation, we specifically evaluate 3 aspects of our design. First is fail crash, that is our design able to detect instrumentation errors at the runtime correctly? Then we measure the performance overhead of our design. And third, we see that if our platform can instrument large or wide range of real world programs. So to evaluate fail crash, we depend on a customized set of core utils. So the customized core utils binaries have data embedded in code. So the table here represents various rules which we have used to identify or classify code pointers. So here we can see that if the function prolog matching and the address translation technique, the runtime address translation technique, are the most effective ones and always result in 100% correct instrumentation. Instruction boundary here means any pointer that is being disassembled into a correct or valid assembly instruction will be considered as a valid code pointer. We can see that its success rate is only 43%. For the rest 60%, we are able to verify that the program fails right at the moment when it is trying to use a data pointer that has been misclassified by us as a code pointer. So similarly, ABI validation here means we check that the pointer respects the system ABI. System ABI basically means the rules that signify which registers are used for call arguments and which registers should be preserved by a callee. So here we can see that since function prolog matching and runtime address translation are mostly accurate and always result in 100% correct instrumentation, they in case of a safe failure, we can re-instrument the binaries with these fallback options to have a correct instrumentation. Now, to measure performance overhead, we have 4 different modes here. The red bar here represents our base mode, that is full address translation mode. In this mode, even the return addresses are go through runtime address translation. No wonder that this always results in correct instrumentation. However, this has a very high performance overhead. The yellow bar here represents the pointer encoding mode, in which every pointer, including the return addresses, are encoded. Now we can see that the encoding decoding operation has 3 times less performance overhead than address translation itself. Now the green bar here represents return address optimization. In this case, the instrumented program is allowed to use the instrumented or the new return addresses. Although this mode is performance friendly, this is incompatible with certain functionalities like C++ exception. So what we do is we update all the exception handling metadata to be in sync with the new code layout or the instrumented code layout. Finally, the blue bar represents our safe jump table analysis results, which results in approximately 2% overhead. For non-PI or position dependent binaries, since we cannot identify or differentiate between constants and pointers, there is no scope of encoding any pointer. So we only have 2 modes, and after applying the safe jump table optimization, we have 5% overhead for position dependent binaries. Now for functionality, we considered around 16 real world applications with 500 plus libraries. Out of 16 applications, 6 applications used at least one library that had embedded data. Out of these libraries, only libgcrypt is the one that had failed crash or say failure. By re-instrumenting libgcrypt with full address translation mode, we are able to run all the applications successfully. So to summarize, Sekar is able to effectively combine pointer encoding with runtime address translation to have a low overhead of nearly 2%. Sekar's novel pointer encoding facilitates runtime error detection. Sekar's jump table analysis helps to improve performance without compromising correctness and safety. Thank you. I'll be taking questions.
Thank you.